sure that chlorine is slowest. Okay.
So you said 1 bromobutane is the slowest.
Second slowest.
Huh?
We have 1 chlorobutane after that.
No, 1 bromobutane. That's the
That will be the second slowest.
second
For
slowest?
SN2,
Yeah.
it's the
For
second.
SN1?
Yeah.
The second slowest?
Yeah. What's the slowest?
Fluoride.
Okay, so like I said, so we don't need a good nucleophile for SN1. So the reason why we're not using sodium iodide anymore is because you saw it. Use sodium iodide, it'll go through the SN2 mechanism, right? So by adding a weaker nucleophile, you can force it to go through the SN1 mechanism. And another thing that will help is remember how for SN1 the leading group just falls off, right? But if you add in something that will take the leading group from you, it'll just make carbon formation that much easier, right? So we have silver nitrate in our part B, and what that does is takes the chlorine from our alkyl halide or the bromine, and that's a precipitate that gives us silver bromide or silver chloride, okay? And that forces the carbocation formation, and our ethanol will be our nucleophile to then attack our products. Questions about that? So are we making the same products with part A and B? No, we have different nucleophiles. We start with the same electrophiles. Okay. So for part C, what we're looking at is solvent effects. And solvent effects matter more for SN1 than for SN2. And the reason for that is because you know that your intermediates are charged, right? You're making a carbocation, which is positively charged, and you have your leaving group, which will be negatively charged. And you don't want these charges to be floating around, right? Positive and negatives, you don't want them floating around. So what our solvents would do is it would make this huge sphere around it and separate the charges so they're no longer destabilizing by these charge repulsions. So water is a great example. So oxygen is electronegative, yes. So we have our carbocation, which is shown as R plus in this. And so you'll see that in this case, all the oxygens are pointed towards the positive, and then all the hydrogens of the water are pointed towards the negative. Right? So they're just making huge circles, and this will keep going on in like rings. You're just separating the charge. And that's good just because you're separating the charge and decreases the repulsions, right? And then helps the reaction faster. So how well a solvent can separate these charges is known as dielectric constant. Okay, and it's just a number. And so water has the highest dielectric constant of 78. And ethanol, and there's a trend right there. Okay, so in our reaction, so higher the dielectric constant, the faster your reaction for SN1. In our reaction, we are adding a mixture of water and 4 other solvents. We have methanol, ethanol, propanol, and acetone. Okay. So based on that, which mixture will give you the fastest rate?
Water and methanol.
Water and methanol, okay. And then?
And water,
Okay.
propanol.
And then?
Acetone.
Propanol's not in there, so where
But
would it come?
it would be in between methanol and acetone.
Ethanol and then acetone, right?
Yeah, sorry.
Oh, okay. And then acetone will be the slowest, correct? And what could be some of the reasons why your trend might not match experimentally? If it didn't match, choose A, let's see. It evaporates. What would happen if I have water and acetone and then acetone's evaporating?
Higher concentration of water.
It's going to be basically just water left, and you know the water is the fastest, right? So just because your data doesn't match, and it probably won't match, don't freak out. Just write down what you see. Know that you know what it's supposed to happen. So regardless of what you see, be able to explain what it's supposed to happen and why. That's all chemistry is. We can't always expect to get anything else. So to summarize, SN1 and SN2. SN1, you don't need a good nucleophile. You don't take anything that's floating around, okay? SN2, you need a good nucleophile because you're kicking out the leaving group. In both cases, you need a good leaving group or else it doesn't work. So the reactivity trend for SN1 tertiary is the fastest because of carbocation stability. For SN2 primary is the fastest because it eliminates steric adherence. You're attacking from the back. For SN1, a good solvent is required. For SN2, there are some rules, but we're not going to get into that. And you can force SN1 reactions by adding an agent that will take the leaving group. what I want you to do is in this experiment, there are 3 parts, A, B, C. Each group has 3 people, so I would like each of you to just pick a part and do it all individually and combine with your own group and share. Okay, there are plenty of test tubes and test tube bags, so it will be more of an individual lab, but in the end, make sure you have data for all 3 of you. Okay. And again, do the experiment in order from fastest to slowest. And so for your report, as far as mechanism goes, I would like you to do, we're not done yet, mechanisms for 2-bromo-2-methylpropane for both SN1 and SN2. So like we mentioned, they'll form different products. You have different nucleophiles. Make sure you also give me the small balanced equation that I showed you. That's what's forming the precipitate. Make sure you talk about all of that. Show me the differences between SN1. So SN1 and SN2. Just because you give me a pretty picture of the mechanism doesn't show me that you know it, because it just means you probably copied it from somewhere. So any figures, tables put in your report, other than table of reagents, need to be talked about in words. Okay? So when you're doing a mechanism, you need to tell me what is forming, what's reacting, what are the intermediates, things like that. Okay? And in your intro this time, I'd also like you to hypothesize the trends that we talked about, just like right now. And so in your discussion, all you would have to do is compare what you hypothesized, and then if it didn't happen the way it was supposed to happen, then just explain what you see. And there are no calculations, so your results are extremely easy. All you have to do is make a table with all the times. So we're not calculating any K values or percent yield or anything like that, so it's based solely on some time. Okay. And your result is, yep.
Where do you want the explanation of mechanisms results?
No, intro. Yeah, so this lab, intro is going to be really heavy, and discussion is so, and results is like just times.
Okay, also I want to point out the test tube racks are on this far side of the left side of the organic lab, so use those. So don't just be standing there holding the test tubes. We have nice racks you can use for that. And also the silver nitrate that you're going to be using, be very careful, because especially if you're like me and really fair complected, then it can stain your skin on it, so you can have like a really nice dark stain on your skin for about 3 weeks or so. So just be really careful when you're using it, and please be careful. And I want, before every group leaves today, that I want you to wipe down your lab bench with water and a paper towel, so that way if there is anything like silver nitrate, anything on the lab bench, that we get it wiped up. Because last thing you want to do is lay your hand down on the lab bench and get it stained on your hand. So just make sure that you clean up really well today. Yeah, that's about it. So any last questions before we get started? All right, go ahead and start.
Sonia, in the lab report, do you want to know what the precipitant looked like in the lab report? That would be in the procedure to put down, like, you know, in part A, test tube, yada yada yada.
No, it just has to be like, it's going to be the same type of presentation.
Okay.
Explain one of them.
Okay, so just explain what it looks like. Okay, for each part, A, B, and C. Okay.
Smaller test tubes is going to be okay for this?
Yeah.
Okay.